during the organization. So just a few announcements. So the coffee breaks are going to be upstairs. We'll have 2 talks which are going to be given. This is the second time he does this to me, because he did the same thing at the WSCP. So the coffee breaks is upstairs. We're going to have a group photo tomorrow, just before the coffee break. There will be a list just after this coffee break for the conference dinner. We'll have a conference dinner on Thursday evening at 7 p.m. This is going to be at Bovinos, which is in Alameda Santos, close to Paulista. The conference is going to pay for the food, so you have to pay only for your drinks. So we'll get a... So if you drink a lot, then yeah, we're not going to pay for that. And we'll have a small change in the schedule on Friday. So Professor Elena Petrilli could not be here. So we'll transfer the talks all to before lunch. So the conference will finish at lunchtime. So that's the only difference. And so we'll reschedule everything to accommodate that. So with that, I think these are all the announcements. Maybe I'll come back for a few announcements. With this, I would like to give the chair to our chairperson, first chairperson, so to introduce the next speaker.
Okay, thank you, Alexandre. And our first speaker is Professor Vera Henriques, who is going to talk about phase coexistence, interface tension, and convexity of thermodynamic potentials. I think you have to put this one on around your neck so that the camera follows you. And then, do you prefer this one?
Não, não sei como faz. Eu tenho que segurar?
Ou então você pode plugar, colocar num bolso, esse bolso serve? Pode ser também.
Sei. Não posso tirar a blusa. E esse?
E aí você põe em algum lugar que... Isso aí, olha. Okay, thank you, Vera, and you can go ahead.
So, I would like to thank Danilo for...
I think it's off, sorry. Let me see this one. Nice.
So I would like to thank Danilo for the invitation. It's really a very nice initiative, this one. My English is a bit... getting together people who work on similar things. I think we lack this in Brazil, and so it's a very nice initiative. So I will speak about phase coexistence, interface tension, and convexity of thermodynamic potentials. This is a... Oi. Mais alto?
Então, também você põe pouco mais para cima o microfone. Não, cadê o microfone?
Ah. Sumiu o microfone.
Aqui, Vera.
Aqui? Tá, então tem que pôr ali. Será que é aqui? Is this better? Well, this is a sort of theoretical question. Oops. It's not going.
Eu não sei nada do show. Talvez eu possa ficar.
It's not working at all.
Qual é a sua apresentação aqui, Vera? Só clica na tela aqui que ele funciona. Pede para eu essa agora.
Mas estamos sem a luz.
Não, aqui tá muito alto. Desce aqui na lousa.
Ah. Oops. Okay. So the plan of the talk is that I'll
I want to mention that thermodynamic instabilities has been a common feature in publications of the last decade, and sometimes allied to the question of ensemble inequivalence. So I'll talk about this point a little bit, and then I will show that the thermodynamic, what it has been considered a thermodynamic instability for coexisting phases. If you do a correct interpretation of the field variables, you don't really have this thermodynamic instability, and we'll show this for the case of the lattice gas and pose some other questions. Oops. So on thermodynamic instabilities, we all know that the second law of thermodynamics says that entropy must be a concave function of its variables, and therefore there is a definite sign for its derivatives. And by analogy to mechanics, this the inverse situation is forbidden, but is called unstable. So it's forbidden, but gets this name in thermodynamic instability. Opa. So the question of thermodynamic instability arises very frequently at phase coexistence, which embraces several different situations, including the very simple situation of phase separation of water and oil, as in the central picture. Thermodynamic instabilities are long known to occur under the mean field approach for phase coexistence with this van der Waals well-known picture, sort of 150 years ago, with van der Waals' proposal for the treatment of the pressure volume isotherms, where you have here the pressure increasing with volume. So this corresponds to a situation, for one of the forbidden situations related to the second law for the Lejeune transform free energy. But this is okay. There is no problem, because in fact mean field treats the system as homogeneous throughout the transition, and therefore it's not a good theory, because in this region the system is two-phase, so you have to treat separately the two phases, and so we ignore this thermodynamic instability there. Well, the question I'm bringing here is that thermodynamic instabilities arise in numerical experiments, and therefore if you have a statistical model at equilibrium, at phase separation, this has been known 100 years after van der Waals by Binder's group. So what we have here, let me show in this picture. This is a chemical potential. This is the density of the system. And the chemical potential should increase monotonically with density. However, if you have phase coexistence in which two densities coexist, you may have here a decreasing chemical potential with density, which again violates the second law, since the chemical potential is the derivative of the free energy with particle number. So we have these groups in canonical ensemble simulations for the phase separating system. Another instability which is frequent in the literature, I just brought a few examples. Here we have the inverse temperature as a function of energy, And the inverse temperature should always decrease with energy because temperature increases with energy, making a positive specific heat. But here we have a paper by the Landau group on the simulation of an elastic polymer, and you have here the temperature decreasing as energy increases. These are simulations in the microcanonical ensemble. So what is the problem here? Just bring two other examples. This is a pot model, and here we have temperature as a function of energy. Temperature decreases with energy, so negative specific heat. This is microcanonical ensemble simulations, and this is canonical. So this instability would arise only for microcanonical simulations and not for canonical. And here, long-range interacting models have also been cited frequently as using inequivalence of ensemble and also instabilities, again here, temperature decreasing with energy. Well, what I will show in the following is that this instability of the chemical potential does not exist. And our work was in part suggested by this picture. This is, again, 20 years after the first study, a study by Binder's group of the Lennard-Jones fluid. We have here the chemical potential again, the density, and the instability, the decrease in chemical potential with density is related to the interface which is formed. You have a gas phase, you have a liquid phase, and there you have increasing interface from a sphere to a cylinder to blocks. Note that when you have blocks, you have flat interfaces, and in this region you have a plateau like it should be. The phase coexistence would be represented by a straight line here, a plateau, and therefore we must explain what are these things, these loops here. So what I have here is the same problem, but with 2G lattice gas. And you can see here that you have a circle forming, which turns into a strip of liquid. Again, a strip, and then the strip collapses to a circle, which decreases in radius. And this interface form is again related to these loops, as we will show. And the solution of this riddle comes with the correct description of the thermodynamics of coexistence. At coexistence, the free energy, the Helmholtz free energy must be described in terms of a sum. Sorry. Where you have the free energy of the bulk, liquid, bulk, gas phase, but then you have a macroscopic contribution of the free energy of the interface. And this free energy of the interface depends on the area of the interface, and with the coefficient which is the surface tension, interface surface tension. So if you have a homogeneous system, the chemical potential is really the first partial derivative of free energy with respect to particle number. But if the system is at coexistence, you have an additional contribution if you just do this first derivative here, you will have a contribution which is really the chemical potential, plus a contribution which depends on how the area of the interface increases with the number of particles. The true chemical potential would have, to obtain the true chemical potential from this derivative, we would have to maintain the area of the interface constant, which is not what we do when we do simulation. So here we can see that for these pictures for which the area of the interface, the volume is decreasing, but the volume of the gas phase is decreasing, but the area of the interface is maintained constant, so that contribution is 0, and you have the true chemical potential here. However, while the interface is increasing in size, here it's a line interface, in fact, because we have a 2D system. So this line, this perimeter of the circle is increasing, so you have a contribution above the true chemical potential is here, and you have a contribution. Whereas you can see also here when the apparent chemical potential is decreasing below the coexistence potential, it's because the interface area or interface perimeter is decreasing, so you have a negative contribution here. So with this interpretation, what we have is that this loop allows the calculation of the interface tension, because the area is the lattice size, be it in 2G or 3G. So if we integrate this, we can obtain surface tension. And I have shown you the lattice gas problem because we have an exact result which we can compare with our simulation data, the exact result by Otaga. So we show here good agreement between the theoretical and analytical curve and the data points. But if we do a size study, we see that our data converge to the exact result. So this means that we have a good way of obtaining surface tension for models. And here I have shown you a lattice model, but it is exactly the same for continuous models. We have a parallel thing, which is the fact that we obtain coincident results in the canonical and grand canonical ensemble, which is a question which has been raised in the literature for several models. So here I just show the same pictures for the chemical potential and how we obtain the chemical potential in the canonical ensemble. It's a well-known window insertion model in which you calculate, you discretize the chemical potential and thus obtain the chemical potential as its average. And if you have, what I'm showing is that if you have coexistence in your system, then when you do this, when you calculate this average, in fact, you are obtaining this sum, the sum of the chemical potential with this contribution of the interface area increase variation. In the grand canonical ensemble, what we do is we're fixing the chemical potential or pseudo-chemical potential, and we can measure the probability of different densities. This is possible only if you use very special simulation Wendell proposals, and because if you are at a low chemical potential, these high density regions are not probable. So very small probability. But we could obtain the full curves. So this is a probability distribution for density at a fixed chemical potential. So we can see here as we increase the chemical potential, the two maxima approach each other. Okay. And from here, we obtain then the relation between density and the pseudo-chemical potential. So here we compare the two results. Here you have the grand canonical result with the three extrema represented here in this chemical potential isotherm, which is the complete line is made from points obtained in the canonical ensemble. And these 3 points are represented here. Here you have coexistence with a plateau here, and when we compare results from both ensembles, we obtain full coincidence to what the eye can see. And also, we have done this also for temperature. If you use the special simulation proposal of Wojtaszek, you can obtain temperature with this thermodynamic instability, and this, in fact, is not the temperature, but a pseudo temperature, and you can correct this part by treating the area, the contribution of the interface free energy. So, in conclusion, true phase coexistence chemical potential in simulation has no loops. Interface tension can be calculated easily in the canonical ensemble, and this is true for lattice or continuous models. And a word of caution, if you have temperature loops, you must look at the role of the interface contribution, besides other things.
Okay, let's thank Vera. Are there questions, comments? Okay, Lucas.
Thank you very much for the nice talk. I would like to ask you about the surface tension. Do you consider like a global surface tension or a distribution of small droplets of surface tension in your model?
We have both cases.
Yeah, I was going to ask what is different.
We consider, in fact, that you have the same surface tension. If you have a fixed temperature, if you have a very small density, maybe you haven't had the collapse on a single gota, a single cluster. So maybe you have more than one cluster. But what we are supposing is that the surface tension, be it on different clusters or on a single cluster, is the same if the temperature is the same in the chemical potential. Okay.
Let me make a comment. In our area, there are some very active people, by the way, who keep publishing papers claiming there is an equivalence between results in the canonical and in the microcanonical ensemble for some systems with long-range interactions, things like that. Well, I'm convinced that they are wrong. I'm deeply convinced. I tried even to publish and provoke them, but they keep publishing those papers, okay? And I think this it's a good point to show the equivalence of ensembles from an appraisal of the numerical calculations. All right? Unfortunately, those people keep publishing those papers. Huh? People who look at the archives realize that they are very active people. Some of them are even my old colleagues. Okay?
Thank you, Vera, for the very interesting talk. So just for me to see if I understand. So suppose you have a water surface, square art, exactly as for the surface tension, this. Yes. Exactly a square as you've shown. And you start putting oil on top of it. And then oil likes to be a circle. And then you start increasing the chemical potential, you put more oil. But then the increase of the interface would be, we know how to calculate it directly, right? And it would always go up. So what can you learn from this using your, what would be the surface tension then? You understand the question?
Yes, but if you are increasing the chemical potential, what I'm saying is the surface tension depends on temperature, okay? And if you have coexistence, in this case you're saying you have water, oil, and you have vapor of water. So it's a sort of three-phase system. What I'm showing is for two-phase. So maybe we would have to treat specially this three-phase system.
Vera, thank you. Very nice talk. What I want to ask you is it fair to say that what you did is the quantitative way of doing something that reminds us of the Maxwell construction? That picture of the force
yes.
that you show when you integrate that looks like...
Yes.
So it's a quantitative way of doing that. Could I say that?
It's a very good...
Thank you.
Very good question, because the Maxwell construction for the mean field isotherms has a different origin, and it's done sort of by hand. Here, you just connect, you say that the method is bad for the coexistence region, and I connect the two, the gas and the liquid phase segments. By the continuity of the free energy, and knowing that you must have a straight line. Here, what we're showing, it is a sort of Maxwell construction, but it's based on thermodynamic, on correct thermodynamics. So yes, we have done this. Yes, quantitatively, yes. Yes, exactly, yes. And on Salina's comment, I would like to comment that we have, for instance, negative specific heats coming from other areas, and very well known in gravitation and other things. So we must understand better these things. I'm not saying that they're wrong. What I'm saying is that we must understand better what is happening. So that's a comment.
Okay, let's thank Vera again.